Welcome back. Let's continue with our preparation for examination. One question again drawn from the past paper. It's question number 5 on a normal question paper, will be involving work, energy and power. Now, according to the question, let's read the statement. It says a load of mass 75 kilograms is initially at rest on the ground. It is then pulled vertically upwards at a constant acceleration of 0.65 meters per second by means of a light inextensible rope. Refer to the diagram below. Ignore air resistance, and that friction is ignored here. Rotational effect and the mass of the rope. This is diagram, you can see. And then 5.1, they say to us for 2 marks, draw a labeled free body diagram for the load while it moves upward. Remember, when you draw this one, because it's 2 marks, the load will be represented by a dot, represent an object with a dot. All free body diagram, don't forget, 1 mark free. All free body diagram will have the weight, or you call it FG, gravitational force. And the second mark, because there's a rope that is pulling the load, then when you see the rope, know that in this section of free body diagram, the rope, the cable, will be now representing the tension. These are the 2 forces. You get 2 marks if you write it in this manner. And then 5.2, according to this one, you can see 5.2, they say, name the non-conservative force acting on the load. Remember, we've got conservative force and non-conservative force. In a nutshell, conservative, we have got only one conservative force, it's your gravity. But whereas non-conservative force, we have got 3 examples there. It will be your friction, kinetic friction, can be the tension, or can be the applied force. Now in this case, what is applicable now, we have got only one that is in this group, non-conservative force, therefore it will be the tension. Just a name, that's okay, get 1 mark for doing that. Next question, 5.3, they say calculate the work done on the load by the gravitational force when the load has reached a height of 12 meters. That's your delta X. Now remember, there are 2 forces that are doing work on the object here. The object is going up, therefore the tension is doing positive work. We'll be using the cosine of theta there. And then the weight is doing negative work, then we'll be using the cosine of 180 degrees. Remember, this will be 0 degrees and this one will be cosine of 180 degrees. That's when you interpret it simply. Now we are calculating the work done by the weight. So there's a formula for work done by a single force. This is the formula. Work done by a single force is the force multiplied by delta X cos theta. Fine, our force is the weight. Now we'll have to multiply the mass. The mass of the load is 75. Therefore, we'll have 75 multiplied by 9.8 multiplied by delta X, which is 12, and the cosine of 180 degrees. We said the weight is doing negative work. That will be the case. And then if you use your calculator, in this case, you must find a negative 8,820 joules. So remember, some learners can use other formulas to say the work done by the weight equals to negative delta EP. Also will give you the same answer. Other people also can use the work done by the weight as mgh cos theta. Also you'll get the same, because this is your delta X. Then the weight also is doing negative work, will be a cosine of 180 degrees. It will be almost the same as this one. So these are the 2 options that you can explore just an alternative, but the easiest one will be this one. Now 5.4, very simple. Now they say to us, if you look, state work energy theorem. Remember, when you're stating work energy theorem, we are guided by the work net equals to delta EK. That's the formula that is guiding us. Therefore, work net has got three expressions. You can go for work done by net force, or the total work done, or the net work done. So let's choose your net work done on an object. That is the left hand side, equals to the change. The delta is change in kinetic energy of the object. Don't be like me and write EK. You can write the whole weight kinetic energy of the object. That is the definition for 2 marks. Fine. The next one will be, remember the keywords there will be the word change and the net. So if you just write the work done, then it will be incorrect. 5.5, which is the one for calculations. You can do it on the next page. Now 5.5. Let's look at the question. They say to us, use work energy theorem. Use the principle that we've stated above. Use a work energy theorem to calculate the speed of the load when it is at the height of 12 meters. Now, remember, when we are using that, if you go back to the free body diagram, there are 2 forces that are doing work on the object. Then we are going to write the work energy theorem first. We are using it. Work net equals to delta EK. That's how you're going to start this. And then after doing that, you'll have to now mention which forces are doing work on the object. So on this one, which forces are doing work on the object? There are 2. Is the work done by tension plus work done by the weight, gravity, which is the same as half mvf squared. Delta is final minus initial. The final kinetic energy minus the initial kinetic energy. Fine. When you have done this, you just have to substitute. In this case, the work net in this case, the forces acting on this one, the acceleration is given. So which means that now we have got 2 options here to say, instead of this, I can use F net delta x cos theta. So then in this case, because acceleration of the system is given, can you see, at 0.65 meters per second. So acceleration of the system is given there. Or if you don't do this way, you have to first calculate the tension using the very same F net equals to MA. Because you know the weight, you can do that. So that's another option. But the easiest would be, now we know acceleration, this is MA. Mass of the whole thing is 75 multiplied by 0.65, and delta x is 12, and the F net is doing positive work anyway, then it will be 0. Then the final will be half of 75 multiplied by VF squared, and then the initial, because it started from 0, we make 0. When you calculate here, use your calculator, you will find the answer to be around 3.949, so 95 meters per second. Remember, this is one option. The other option, the learner, you can as well also opt for going for tension first, to say F net equals to MA, and then the tension minus the weight equals to MA. You substitute tension minus weight will be 75 multiplied by your 9.8, and then equals to 75 multiplied by 0.65. You first find the tension, then which will be somewhere around 783.75 Newton. Then once you know the tension, you can come back to this one and say work done by tension. Then you find that one, you are going to subtract from the work done by the weight that we calculated, which is 8820. Then you will find. So if you work and say from here, now the choice will be yours to say, okay, fine, work energy theorem, they will be the same as delta EK, and then work done by the tension plus work done by the weight equals to your half mvf squared minus half mvi squared. So work done by tension will be your tension 783.75 multiplied by delta x, which is 12, multiplied by the cosine of 0 degrees, then plus negative the work done by the weight 8,820. Then you will find that one of half of 75 multiplied by f squared minus 0. You will get the same answer as Vf will be 3.95 meters per second. That's how alternatively you can do that. So that is this section of work, energy and power. Hopefully you have learned something out of this activity, especially doing using work energy theorem if acceleration is given, or also dealing with the work done by the weight if the weight is doing negative work. That's the case. So until we meet next time, thank you. Bye.